want to just review one or two of the questions on the bending equation tutorial sheet. And we'll pick out ones in particular that you may want to have a look at, and we'll go through those. And then we'll look at the section modulus, which is the last part of that second handout you've had, and the use of that table in there to find the correct I-beam to use in a structure. And then we'll move on to the next handout, torsion in shafts, which actually involves equations that are almost exactly the same as the bending equation. So we'll be carrying on looking at the tutorial questions in there, which are exactly the same idea as the bending equation. So let's start off by having a look at one of the tutorial questions in the bending equation, this one here, number 5, and think about how we might go about doing this one. Okay, so let's start by drawing it out, put on what we know, and then think about what the bending equation is and which part of that we're going to be using. Okay, so we've drawn it out. This thing is bent. If we think back to the initial conditions for this bending, the use of this bending equation, they were that if we bend the beam, the cross-section area is the same all the time. There's no warping going on, and there's no twisting or anything like that. And in this case, the radius of curvature is taken to always measure to the neutral axis. So in this question, it doesn't say anything other than that. So we assume that the radius of curvature is measured to the neutral axis, which runs through the middle of the beam. We're also given the maximum stress that this can take, this particular beam, and Young's modulus, values for Young's modulus. And we've got to determine the dimensions of the section. So we need to calculate B and D. So now we write down the bending equation, which is just a series of ratios. So the ratio of the stress to Y, and remember what Y is, it's the distance from the neutral axis to the top of the beam. So in this case, and in most cases, Y equals half D. So the ratio of stress to Y is the same as the ratio of the M, which is the moment, over I, which is the second moment of area, and that's the same as the ratio of Young's modulus to the radius of curvature. So now we decide which of those ratios we're going to use and which one we're going to discount, which is the one that's not useful in this scenario. M over I, yeah, we don't know the moment and we're not interested in the second moment of area, so this particular ratio is not used in this question. So those are the two we're going to use. Sigma over Y equals E over R. Remember, we're after the dimensions of the thing, so once we know Y, that's the key one. We want to find Y, because once we've got Y, we can find D and B. Okay? So we rearrange these remaining ratios to enable us to find Y. So sigma over Y equals E over R. So therefore, switching the ratios around, Y over sigma equals R over E. And now we want Y, so we multiply both sides by sigma, the stress, and we get Y equals R over E times the stress. And now all we've got to do is put in the values and we can work out Y, and from that the dimensions of the beam. So I'll leave you to finish that question off.